this has been for both a simple pendulum and a physical pendulum. Now is when we need to differentiate between the two, and again, we're going to do the simple pendulum first. So let's go to a new slide here. So for the simple pendulum, which again is just a point mass at the end of a string, we can ignore the mass of the string. For a point mass at the end of a string, simple pendulum, the moment of inertia is just ml squared, okay, where m is the mass of the pendulum bob. So if we substitute that into our angular acceleration equation, we're going to get that alpha is going to be equal to mg theta L over m L squared. Simplify, and we get that alpha is equal to g times theta over L. If we look back at the last slide, if we get another equation for alpha, alpha is also equal to the negative of the amplitude. No, that's not right. Alpha is equal to, let's get this out of the way. Alpha is equal to omega squared times theta. Okay, if we look back at our last slide and rewind. Just like in the linear version, linear acceleration is omega squared times linear displacement. For angular, we have alpha equals omega squared times theta. So we have two expressions for alpha. We're going to set them equal to each other. We're going to say that omega squared times theta is equal to g times theta over L. We can cancel out our thetas, and we can find that omega is equal to the square root of g over L. So what all this has been leading up to is another expression for the period of a simple pendulum. We know that t equals 2 pi over omega, so we can plug the omega that we just found in, and we can say that the period of a simple pendulum is 2 pi times the square root of the length of the pendulum over the acceleration due to gravity. Again, notice what's not in here. The mass of the pendulum bob is not in here, so you could take a really heavy pendulum, a really light one. As long as they're the same length and at the same location, they should have the exact same period. Okay, so this is our end result. That's what all that derivation was for. This is the period for a simple pendulum. What else you need to know here? You need to know the angular displacement function. So one of the very first things we did, you need to know that theta equals theta max times the cosine of omega t. The rest of this really just derivations here. Okay? Again, this is for a simple pendulum only. If we have a physical pendulum, we can do something similar, and we can find an expression for the period of a physical pendulum. To spare you the derivation of it, the period of a physical pendulum is going to be equal to 2 pi times the square root of the moment of inertia, so moment of inertia matters now, over mgh. And h is the height of the pendulum. This expression, we've got the height of the pendulum, not the length of the pendulum. So if we had our, let's say we got a meter stick or some kind of rectangular object, we would care about the pivot point at the end. We would care about the center of mass. And h is going to be the distance, not from the pivot point to the end of the pendulum, but h is going to be the distance from the pivot point to the center of mass. Okay, so not the entire length of the pendulum. H is the distance measured along the pendulum arm between the center of mass and the pivot point, so between pink and yellow here. Okay, so that distance h, not the length of the pendulum. Okay, so that means it probably will not cancel with the distance in the moment of inertia. Okay, if you plug in for moment of inertia, you're going to want the length of the pendulum, so that would be L. Okay, so if this is a rod rotating about its end, its moment of inertia would be 1/3 ml squared, you could not cancel that with h because those are different distances. So if you have a physical pendulum, sometimes the algebra becomes a little complicated, but it remains just algebra. So let's try a sample problem that hits at both a physical pendulum and a simple pendulum. We have a meter stick swinging about a pivot point, and it's a distance h, so that's convenient for our formula. The pivot point's a distance h away from the center of mass. Okay, so our pivot point is going to be up at the top here, and our center of mass in white will be right at the center of our meter stick. So if we have a nice uniform meter stick, which we do here, the center of mass will be exactly half the length of the meter stick. This is going to swing in a nice circular path here. We'll treat it as a small enough angle to be in simple harmonic motion. And the first thing we want to know is what is the period t of this meter stick. Okay, again, this is a physical pendulum because it's not just a point mass at the end of the string. This is a physical pendulum, so we're going to need our period equation for a physical pendulum, which is going to be t equals 2 pi times the square root of the moment of inertia I over mgh. Okay, where h again is the distance between the pivot point and the center of mass. Okay, so this is h. And we know that the total length of this meter stick is, we'll just call it L. So h, if we look at the uniform meter stick, h is going to be 1/2 L. So if we start plugging in to our period equation here, t equals 2 pi, the moment of inertia of a uniform rod rotating about one end is 1/3 ml squared, and we can say mgh at the bottom, where h is 1/2 L. We can cancel out the mass. Okay, so again, we see that mass should not matter for a pendulum. Working with these fractions a little bit, we can move the 2 to the top, the 3 to the bottom. We can cancel out 1 L from the top and the L from the bottom. So the period of this is going to be 2 pi times the square root of 2L over 3G. I'm plugging in. We know the length is 1 meter. And then we have 3 times 9.8. Plugging in, we see that the period of this pendulum is going to be 1.64 seconds. So that's our answer to part A, 1.64 seconds. For part B, we want the length of a simple pendulum that would have the same period that we just found. So we want to use our simple pendulum formula. For a simple pendulum, we know that our period is going to be 2 pi times the square root of L over G. We want to plug in 1.64 for our period, and we want to solve for L. So we're going to do that. 1.64 equals 2 pi times the square root of L over 9.8. Again, we don't have our meter stick anymore. We have a simple pendulum. So we don't know the length. That's what we're solving for. We know everything other than the length, so it's just a matter of doing the algebra out. And that we get that L is 66.7 centimeters, or 2/3 the length of the meter stick. That's going to do it for this video. Please remember, this is not a substitute for reading your textbook. It's not a substitute for doing the example problems in your textbook. Your textbook works out some sample problems for you. Please make sure you're reading through those. If you still have questions after watching this video, after looking at any of the other resources I post up on Schoology, please send me an email. Do not leave this assignment for January 1st. Enjoy the rest of your break, guys.